Recording is live. And for those of you who came late, I'll give you your exams after the class or whenever I take a little break to do a sample question. Let's move on to our next big topic. This is what's known as thermochemistry. Now, straight off the bat, tomorrow's lab is a workshop on this topic. So, of course, the priority today is getting all the content out. We will have time in tomorrow's lab to get some practice done with some questions. Thermochemistry can be loosely described as a study of the energy of a reaction. So far in this class, we've talked a lot about the nature of reactions. We've talked a little bit about how to predict the products of a reaction, how to write various types of reactions. We've even talked a little bit about reaction metrics such as yield, stoichiometry, molarity, and the like. Now we're switching gears a bit to talking about the energy of a reaction. Now, to understand a little bit more about the energy of a reaction, let's first identify a generic reaction. Here I've written my abbreviation reaction as RXN. A generic reaction such that A turns into D. We know our left-hand side is our reactant side. We know on the product side, our right-hand side is our products. So for a generic reaction that just involves a conversion from one chemical to another, we can actually have the following statement, which states that energy is either released or absorbed. Most reactions release or absorb negligible amounts of energy. What do we mean by that? Well, what it literally means is that there is an energy associated with every reaction, right? These molecules need to have energy to react with one another. This energy is, of course, where they get their speed from. But not every reaction has a noticeable energy release or absorption. For instance, when I think about a noticeable reaction, I think about the concept of a hot or cold pack. We've probably seen these in the stores. If you're an athlete, you've probably used this at one point or another. The idea is simple. You go buy a cold pack from the store. Normally it instructs you to either break it or rip it, or maybe, I wouldn't say punch it, but do something to the pack that allows it to start getting cold. This is an example of a noticeable release or absorption of energy. In the case of a cold pack, we overall absorb energy. In the case of a heat or hot pack, we overall release energy. Some reactions, of course, have much more noticeable amounts. One of the most common examples of a reaction that releases high amounts of energy is, of course, a bomb. But on the other end, we have reactions such as the formation of carbon dioxide and water within our body. Of course, that doesn't necessarily force us to get colder or hotter, but the energy associated with it is negligible. Since this falls into one of two categories, one where energy is either absorbed or released, we need to have vocabulary to talk about these concepts. The first one that we look at is an exothermic reaction. In an exothermic reaction, energy is overall released. When this happens, such as in a heat pack or hot pack, we see the temperature also increase. Now, remember, if these changes are negligible, sometimes they can be incredibly easy to notice, such as a bomb or a hot pack. Sometimes you may not notice it to the naked eye. For example, if the temperature of a reaction is only increased by 1 degree, it's unlikely that you'd have noticed the 1 degree change, but it may overall increase no matter what. In the case of an exothermic reaction, what we say is that energy exits. And it is from this term exits that we get exo. So an exothermic reaction, energy exits. This is most notably seen or confirmed with that of a negative energy value. In this case, although the negative is, of course, a mathematical calculation here, the negative refers to the direction of energy, that it's overall exiting. In contrast, we have what is also known as an endothermic reaction. You're probably already able to make the assumption, the big guess, that if exothermic releases energy, in an endothermic, energy is overall absorbed. And just as it is the polar opposite of exo, in an endothermic reaction, temperature overall decreases. And what we say is that energy enters. That's, of course, where we get the endo in endothermic. Again, exo, energy exits, endo, energy enters. In this case, what we expect is a positive energy value. So now we have the vocabulary to describe a reaction, depending on whether or not it absorbs or releases energy. All that's left is to understand one final concept, which is the standard enthalpy of formation. You see, the thing about energy is that the word energy is very broad. You can refer to various types of energy. If you've ever taken a high school physics class, then you may have heard of potential energy. Maybe you've heard of kinetic energy. There's various types of energy. So within the context of chemistry, we refer to it as enthalpy. So to be absolutely clear, the word enthalpy is interchangeable with energy, but it's the specific term we use to make it clear what we're talking about, which is when we talk about the standard enthalpy of formation, it is literally the energy needed to break or form a compound. Every molecule, every compound in the world has some amount of energy associated with it to either break it or form it. The standard enthalpy of formation describes this energy. It is given the symbol delta H, where delta is the Greek letter D, delta is in the triangle, and it has the units kJ over mole. Now, this is the first time we're seeing J. J, of course, stands for joule, which is the SI unit for energy. Just as we've seen mass is grams, volume is liters, pressure is ATM, the SI unit of energy is joules, where the K, of course, refers to kilojoules, just as you would use kilograms or kilometers. Now, armed with this information, armed with this vocabulary in mind, how can we use this information? Let's do a sample question. Based on the following reaction, C3H8 plus O2 to give us CO2 gas plus H2O liquid. If we balance it, we just put a 5 there, a 3 there, and a 4 here. Many of us should recognize this reaction archetype. This is, of course, the reaction between a hydrocarbon and oxygen. This is, of course, a combustion equation. In a combustion equation, the products will always be carbon dioxide and water. Identifying that in this context doesn't quite help you for the question, but of course, this provides some context. The question simply states, what is the energy associated with this reaction based on the following? Now I'm going to give you some values. These are constants that will be part of the question. Delta H of C3H8 is equal to negative 103.8 kilojoules over mole. Delta H of CO2 is equal to negative 393.5 kilojoules per mole. And delta H of H2O is equal to negative 285.8 kilojoules per mole. I've given you these in a different color, purple, to make it clear these are values I would give you. These are not values that you would calculate yourselves or know. These are values you'd have to be given. Let's understand what each of these values are saying. Remember, what is delta H? Delta H is the standard enthalpy of formation, which is the energy needed to break or form a compound. So to read this, what we literally say is that to break or form C3H8 is negative 103.8 kilojoules. The energy needed to break or form carbon dioxide is negative 393.5. The other thing I want you to notice is the fact that I've labeled these as negative. Remember what that negative means. It refers to the exo or endo nature of it all. An exothermic reaction is negative overall. This is a case where energy is overall released, aka exits. So being able to read these energy values or terms is incredibly important, because taking water as an example, what this is saying is that the energy needed to form water overall releases 285.8 kilojoules per mole. Now let's actually do it. To calculate the energy associated with the entire reaction after given the energies of specific chemicals, the equation is a standard delta H of the reaction is equal to delta H of the products minus the delta H of the reactants. This is a brand new equation you have been given. This is how to calculate the energy of a reaction. It is the difference in energy between the products and the reactants. So let's see what that looks like. We already seen the equation. We know what the reaction equation is. We see that we have on the product side, we have CO2 plus H2O. On the reactant side, we have delta H of C3H8 minus the delta H of O2. Look carefully at what I've written here. Not only are these the products, but I'm summing them together. Not only are these the reactants, but I'm summing them together over here as well and taking the difference in their energy. In other words, to calculate the energy of the reaction, it is the difference between the energy of the products and the energy of the reactants. As I'm writing, you should note the stoichiometry of the reaction. You see here, I've given you in purple the energy needed to break or form one molecule of C3H8, of H2O, of CO2. But in the reaction itself, we don't just have one of everything. I mean, sure, we have one C3H8, but we have 5 oxygen atoms and we have 3 carbon dioxides. So we need to incorporate that into the equation. For the CO2, we'll put a 3 in front of it. For the H2O, we'll put a 4 in front of it. In front of the O2, we'll put a 5 in front of it. Where do these numbers come from? They come from the balanced equation, the stoichiometry. Now we're going to plug in our values. Starting from left to right, we have 3 times negative 393.5. Added to 4 times negative 285.8. Minus the delta H of C3H8, which is negative 103.8. Recognize where I'm getting these numbers from. Remember, they've been given to you as part of the equation, as part of the question. So it's just a matter of identification, plugging in, and then chug. But as I continue to write, we notice that I did not give you the energy of the oxygen. This is on purpose. In fact, the reason why I didn't give it to you is because elements, as well as diatoms, such as oxygen, possess a delta H of 0 kilojoules per mole. In other words, the fact that I didn't give you an energy with it should be the indicator that it has no energy associated with it. So elements, just straight elements and diatoms, possess a delta H of 0. So here we would just write plus 0. Now that we have this entire thing in full, we can plug it into our equation. Starting on the left-hand side, we have 3 times negative 393.5. Added to 4 times negative 285.8. All of that minus on the right-hand side. Looks like we have negative 103.8 plus 0. For a whopping total of negative 2,200. Let me write that down carefully. Negative 2,218. Is it 18? Yeah, 18.7. Do we know what the units are? Yes, we do. I've given you the units of the individual energies, and they've just been adding and subtracting from each other. So that's how we know the units overall are kilojoules over mole. This is the energy associated with the reaction. In other words, the combustion of C3H8 has a negative 2,200 energy associated with it. What else can we deduce about this reaction? Well, the fact that it is overall negative is what tells us this is an exothermic reaction. The fact that the energy is negative overall is what tells us this is an exothermic reaction. It releases heat overall. Energy exits. So thermochemistry represents what I like to call a marriage between experimental evidence and theory. Recognize that I have to give you the energy values, right? These are known values. You could probably find them in the back of your textbook. I'm not going to ask you to memorize them. I will give the energy values to you. Basically, all right, labeling, you just need to know, okay, it's products minus reactants when you include stoichiometry. Let's try another one. Another reaction, the reaction between silicon and iron oxide gives us silicon dioxide and iron. The question, of course, is what is the energy associated with this reaction? What is the energy of this reaction? I can shorten it up a little bit. I will provide to you the delta H values. The delta H of iron oxide is approximately negative 822.2 kilojoules per mole. The delta H of silicon dioxide is approximately negative 859.4 kilojoules per mole. And those are the only two energy values I'm giving you. Something that we're immediately able to deduce is that I've only given you two energy values. Recognize that the other compounds, the other chemicals involved are straight up elements. They're not in a compound, they're just by themselves. We have silicon and iron. Since they're just elements by themselves, they will have an energy of 0. So they will not be really incorporated, not significantly anyway. So we can jump straight into the equation. We know that the delta H of the reaction is equal to delta H of the products minus the delta H of the reactants. We've been doing this a couple weeks now. Remember that these subscripts are labels. I've written P for products, R for reactants. And we're going to plug this in. We're going to write out the equation in full first. What are our products? Well, on the right-hand side, we have 4 irons and 3 silicon dioxides. Need to make some space for myself. Let me write it over. Minus, on the reactant side, we have 3 silicons and 2 iron oxides. Now that we have the full equation, we can start plugging stuff in. Remember what we pointed out. We pointed out that the elements, silicon and iron, are just elements. So they do not have an energy associated with it. So we can just immediately cross those two out. Not even going to think about it anymore. With that in mind, we can then complete the equation. This is going to be 3 times negative 859.4 minus 2 times negative 822.2 Remember that the elements, iron and silicon, have an energy of 0. That's why we just delete it, right? 0 won't affect our calculation overall. Now we're going to plug it into our equation. We have on the left 3 times negative 859.4 minus 2 times negative 822 point, what's that number? 22.2. When we plug it into our equation, we've got a very nice, easy negative 933.8 kilojoules per mole. And of course, the one thing we can immediately say about this reaction is that it is an exothermic reaction. Where does that come from? It comes from the fact that it is a negative energy overall. Remember that the negative energy value is, of course, a reflection of the math, but the initial values that we've been given are also negative. Those are values you will be given. In those cases, the negative represents the direction. Do we have any questions so far? Great. Our next topic under thermochemistry is energy profile diagrams. Energy profile diagrams are what allow us to visualize the energy of a reaction. We're going to go ahead and actually draw 2 graphs. I'm going to give you time to draw it yourself, and then I'll label the X and Y axes. We're drawing 2 graphs. On the left-hand side, we will be drawing the exothermic graph. On the right-hand side, we will draw the endothermic graph. In both cases, the axes are identical. The y-axis is energy, which is, of course, in kilojoule over mole. In both cases, the y-axis is the same. And in both cases, the x-axis is also the same. It's time, which, of course, time can be in seconds, minutes, hours, or days. Now, for the case of an exothermic reaction, we know at the very, very beginning of the reaction, we should only have products. At the I'm sorry, not products, reactants. At the very beginning of the reaction, that very instantaneous time equals 0, we should have nothing but reactants. After some amount of time has passed, in theory, we should have nothing but products. Those products have an energy value lower than the reactants. In stark contrast, in the case of an endothermic, although we do have reactants at the very beginning, the difference is the products are higher in energy overall. So the reactants are on the left of the graph, the products are on the right. The difference, of course, comes from which one's higher or lower. Now, I like to think of these reactions as quite literally a hike, that these reactants must overcome a hill, get to the highest point of the hill, and then it's a downward slope all the way down. In fact, I don't just think that, I know that. The traditional profile diagram takes that of a parabolic curve looking like so. The reactants have to overcome a hill, and then after that hill is a downward slope to the product side. The same thing can be said for the endothermic, where again we have that hill that leads to the products. In both cases, the reactants have to overcome a hill. And this is one of the reasons I do really liken it to that of a hike. Traditionally speaking, the hardest part of the hike is the incline. It's getting over that hump to begin with. We, of course, know that if we looked at ever going on a hike, it says, what's the highest elevation? What's the elevation change? What's the steepness or whatever? In the same way, we're curious to know what is that energy difference? In other words, how much energy, how much of that hill does the reactant have to overcome? This value is what's known as the activation energy. It is the amount of energy the reactants have to overcome to even make it to the product side. If you don't have enough energy, you can't get over it. Just as though if you don't have enough energy to walk up the 10-mile incline of a hike, you're just not going to be able to complete it. The other facets of this graph that we're interested in is the difference in energy between the reactants and the products. But we already know that energy. That's actually just delta H of the reaction. The difference in energy between reactants and products. The very tip of the graph, the quite literal highest point of the graph, is known as the transition state. Now let's define some of these useful key factors about these graphs. Starting with a transition state. The transition state can be thought of as the assumed middle of the reaction, the halfway points. Remember that the transition state is that highest point over the hill. It's what they have to overcome. It's the peak of the hike. The transition state tells us that on the left-hand side, reactants are being broken. It also tells us that on the right-hand side, that is after you overcome that highest point, products are being formed. And the other new term we introduced was the activation energy. To put it simply, this is the amount of energy needed to jumpstart the reaction. Such that if your molecules have insufficient energy, no reaction will occur. Now, understanding these graphs helps us understand reactions. I mentioned earlier how thermodynamics represents a marriage between real data and theory. This is a good example of that. You see, you would theoretically know the energy values of the reactant and product. You would be able to calculate the energy as we did over here. And then you'd be able to draw the graph. So let's actually do that. For one of the questions we just did, the silicon and the iron oxide, let's do a follow-up part B. Let's say the question simply says, draw an energy profile diagram. All right. Well, we know basically what the graph is going to look like. We know that the y-axis is energy, which is in kilojoules over mole. We know that the x-axis is time. No reason to believe it's in seconds, minutes, or hours, so we're just going to leave it at time. We know from our calculations that the reaction is exothermic. We know what an exothermic reaction diagram looks like. We know that the reactants are higher than the products, so let's draw that in. Reactants on the left, higher than the products on the right, all of whom are connected via that slope. We know, of course, that the difference between the tip and the reactant is the activation energy. That's just a label. And we know the energy difference between the reactants and the products is delta H of the reaction. Now, wait a second. Technically speaking, don't we know this? It's something we calculated. So yeah, we do know it. Negative 933.8 kilojoules per mole. And that's all I would really expect from you for such a question. It's having you identify ultimately, is this exothermic or endothermic? And if it is, what does the graph look like? What is its delta H? So for that reason, it's not that you need to memorize these graphs, but if asked, I could say, draw an energy profile diagram for the following reaction, in which case you would need to be able to identify, okay, that's exothermic, and I know what that graph looks like. Any questions? Yes, Paul. Yes, I would put in the instructions. Please label the axes, the transition state, the activation energy, the delta H. I could provide you with the exact number of the activation energy, in which case you would need to write the number as well, but most likely I will not give you the number. The only real number that you'll be working with is a delta H of the reaction. Good question. Anyone else? Okay. We spent a lot of time talking about the theory of it all. We spent a lot of time developing our vocabulary, endo versus exo, transition state, activation energy, drawing graphs. Now let's look at the experimental side of things. Let's talk about calorimetry. Calorimetry is the experimental technique that is used to determine the energy of a reaction. Now, one of the biggest concerns with this type of topic, we're talking about energy of a reaction, should be to no one's surprise that temperature affects things. It's very sensitive to temperature. We've talked about how exothermic releases and how endothermic enters or absorbs. So this topic is very sensitive to temperature. So how exactly do we devise a technique that recognizes that sensitivity, but isn't affected by simple changes? Meaning, I should be able to run the reaction in a lab room. I should be able to run a reaction outdoors, and the results should be the same, even though they would be two different temperatures. The way we do that is we use styrofoam cups. See, styrofoam as a material is very well insulated. So when we talk about calorimetry, what we're literally doing is we're nesting those styrofoam cups. And what do I mean by nesting? If you've ever seen or heard of those Russian dolls, they're just one after another as they get smaller. The same idea. You put two styrofoam cups together, you get what's known as a calorimeter. A ridiculously simple setup. All you need to do is go to the store, purchase a pack of styrofoam cups, put them in one another like nested Russian egg dolls, and there's your very valid experimental calorimeter. Why? Because it's incredibly well insulated. So the experimental side of it is actually really, really simple. You see, you've run reactions before in lab. You've done stuff where you've made precipitates. In the last couple of weeks, some of you have made products that will dry and be filtered. You've run reactions in beakers and flasks before. Calorimetry just says we're running it in a styrofoam cup because a styrofoam cup is very well insulated and is not immediately affected by temperature changes. With this technique comes a new formula, Q equal MC delta T. With a new equation comes new terms. Q is described as the energy of the reaction, aka measured by the calorimeter. This is traditionally in joules. M is the mass of sample present. Remember, you're adding two chemicals together. There is a weight or volume associated with it. We measure in terms of mass. Delta T is the change in temperature. This is traditionally in Celsius. And capital C is a constant. It is what's known as a specific heat capacity. And since we will be working with water, the specific heat capacity of water will always be 4.18 joules over grams Celsius. So an simple setup follows a simple formula. To calculate the energy of a reaction, you run the reaction in the styrofoam cup. You measure the mass of your chemicals. You know your constant, and you measure the temperature change with a thermometer. Plug those values in. It's an incredibly straightforward setup to determine the energy of a reaction. Let's see what such a question would look like. The question reads, a reaction was carried out in a calorimeter and raised the temperature of the 11.2 gram sample, from 50 degrees Celsius to 77 degrees Celsius. The question simply writes, calculate Q. Okay, so the mere fact that the question outright states the reaction was carried out in a calorimeter is what tells us we will be using this formula, MC delta T. From that formula, we're being asked, okay, I'm trying to find Q, that's equal to MC delta T. Do I know mass? Yes, the question told me it's 11.2 grams. Do I know specific heat? Yes, that's that constant 4.18. Do I know the temperature change? Yeah, I know that it goes from 50 to 77. So now I just need to plug this all in. The mass is 11.2 grams. The specific heat is 4.18 joules over grams Celsius. And then the temperature change is the difference between the two energies, aka 77 minus 50. Where, of course, this is the final temperature minus the initial temperature. We're going to plug this into our calculator. 11.2 times 4.18 times 77 minus 50. Looks like we have a really big number here. This is equal to 1,264.03 joules. How do we know it's joules overall? Well, let's look at the units. The grams from the mass will cancel out with the grams of the specific heat. The Celsius from the temperature cancels out the Celsius of the specific heat. And all we're left with is joules. Now, there's something here you should notice that maybe it doesn't piss you off, but it's like a little bit of a red flag. In one of our previous topics, gas laws, I made very specific claims about temperature. I said to you very specifically, temperature has to be converted to Kelvin. The reason for this was mathematical. Sometimes you might deal with a negative energy, a negative temperature, or sometimes the temperature will be 0 degrees. You put that into any formula, you get some kind of syntax error. But in this case, I didn't convert to Kelvin. Why is that? Well, if I did convert to Kelvin, meaning if I did add 273.15 to each of these, then the temperature would have become 323.15 going to, looks like 340, not 40, let me put in my calculator. I don't want to make a mistake with the math. 273.15 added to 77, looks like 350.15. Let me just make sure the same thing for the 50. 50 plus 273.15, 323. The reason why we don't need to convert it here is because the equation requires temperature change. The temperature change between 50 to 77 is 27. The temperature change in Kelvin, 350.15 minus 323.15, is also 27. In other words, the reason why we don't need to convert to Kelvin is simply because it doesn't change our change. Whether it's in Celsius or in Kelvin, the temperature change is 27. Whether that's 27 degrees or Kelvin, doesn't quite matter. It's 27. So for gas laws, you have to convert to Kelvin. For thermochemistry, it doesn't matter. Whether or not you convert to Kelvin will not affect your overall answer because it happens to work out every single time. Do we have any questions on calorimetry? Remember, the focus of today is to get a lot of the content out. Tomorrow during lab, we're going to get some workshop practice done. We're not done for today. We still have one more topic. But if it seems like a lot of content coming in right now, don't get too bogged down. Once you see some questions tomorrow, you'll see exactly what they look like. Our next topic is Hess's law. Hess's law tells us that if we wanted to calculate the energy of a reaction, here we have A plus B to give us CD, that there is an associated energy of this reaction. But Hess's law believes that A and B can go through what's known as an intermediate, another step before going to C and D. I liken this to just a general commute, and you'll see what I mean in a bit. Just as there is an energy associated with the overall equation, there is an energy associated with each individual sub-reactions, here written as H1 and H2. Hess's law states that the energy of the reaction is equal to the sum of the individual energies as well. What this looks like, if I were to put an analogy to it, let's say I wanted to go from home to the back. But on my way, I decide, hey, I need to get some gas. To go from home to the gas station will take me 5 minutes. To go from the gas station to the bank will take me 10 minutes. Now, with this very simple analogy, how long is the commute from home to bank? 15 minutes. This is basically the premise of Hess's law. Not counting the time actually spent filling up gas, but just the commute, the total time taken is equal to the individual times summed together. Let's see what that looks like in the form of a question. The question says, using the energies below, calculate the delta H of reaction for the following equation. I'm going to put it in a different color to make it clear that this is our overall equation that we're trying to find. It is the reaction between nitrogen and oxygen to form nitrogen dioxide. And the specific equations we've been given are N2 plus O2 to give us 2NO. And the second equation we've been given is 2NO transformed into 2NO plus O2. And in each case, I will give you an energy associated with it. The energy of reaction A is 180 kilojoules over mole. The energy of reaction B is positive 112 kilojoules per mole. So we are trying to find the overall energy of this reaction right here, and we're given the energies of individual reactions below. What we are going to do is we are going to add these reactions together, just as we did up here. The overall reaction is just the sum of the individual sub-reactions. We're going to add it all together. But we need to be sure that everything is correct. For example, in the big equation, NO2 is a product. But in reaction B, NO2 is a reactant. This is a problem. It doesn't quite match up. We want it to look exactly like the top equation. I mean, take, for example, N2 and 2O2. N2 and 2O2 are reactants, and we can see that N2 and O2 are reactants in A. So that's fine. But we need to do something to B to make it look like what we're expecting. And this is just a very simple flip. We are going to flip this equation, literally transforming left and right, such that this is 2NO added to O2 gives us 2NO2. By flipping the equation, we get the chemical on the desired side. I see your hand, Ryla. I'll be there in a second. And whatever we do to the equation, we also do to the energy. Remember this when I told you that the signs just refer to direction? How do we flip the positive? Positive just becomes negative. Ryla, what's your question? Let's think about that. If we flip reaction A, in doing so, yes, we do get the NO on the left, but we now put the nitrogen and the oxygen on the right-hand side, which no longer matches our final reaction. So we're using chemicals we see to identify what to do. Now, Ryla, you probably are thinking, well, what the hell do we do with that 2NO? Look at what happens here. Reaction A forms NO. Reaction B immediately uses it up. So overall, it cancels out. A chemical that is formed in the middle is immediately used up. That's how we know they get canceled out. And when we add these terms together, N2, well, there's no other N2 anywhere, so this is just flat N2. Looking at oxygen, well, would you look at that? There are 2 oxygens on the reactant side. When added together, this is 2O2. On the product side, we have 2NO, nothing added there. This is 2NO2. And lo and behold, that matches our given reaction to the T. You see, it isn't enough to just add the reactions together. In some cases, we will need to manipulate the equation. We can see here in B, we had to flip it. And just as we added the reactions together, guess what we're going to do to the energies? We're going to add them together. Nothing happened to reaction A, so it's still 180. We're going to add it to reaction B, which is now negative 112. Upon adding them together, put this in our calculator, we get approximately 68 kilojoules per mole. And this is the utility of Hess's law. It takes a simple idea. The total time, the total energy taken is a sum of the individual energies. But occasionally we will need to manipulate the given equations to get to that energy. We're going to end lecture for today. We have a workshop on thermochemistry tomorrow. I do expect this topic to be confusing in this moment, but come tomorrow, we're going to get some good practice with it and the math of it all. Good luck. I'll see you all tomorrow. I still have some of your exams. Come to me right now so I can pass them out. If not, see you guys tomorrow. Yes.